So what we're going to do now is kind of visualize how these hook methods work, and then we'll talk about the code in a second. You'll see the code as part of the visualization. The particular example we're going to look at is the one that's the parallel streams example. This is a result that came from running this program actually a couple years ago on an earlier laptop I had that only had 4 virtual cores instead of the 8 cores I have, but it still demonstrates the benefits of parallel processing. And just very, very quickly, we'll go through this in more detail later. Here's the performance of searching for phrases in the complete works of Shakespeare with a sequential stream, and you can see it's about 2,000 milliseconds. And then when we cranked up this thing and ran it in the parallel streams model we're about to look at on the quad-core hyper-threaded processor, it executed in roughly 437 milliseconds to do the same work. And if you do kind of do the math, you'll see that that's roughly a little bit better than linear improvement. Its speed up is about, as many cores as there are. And the reason why it's better than linear is because these are hyper-threaded cores. So they can actually do a little bit better. They're not as good as having, 8 physical cores, but 4 hyper-threaded cores, as you can see, can get you super linear speed-ups in the number of cores. So that's good. And it turns out that there's even faster ways of doing this stuff to speed things up even more. This also demonstrates, to some degree of precision, the overhead of using streams versus just using a loop. So there's also an implementation that uses loops, so it's really stripped down. It's about as fast as you're going to get it in Java with sequential processing. And you can see it's a little bit faster than a sequential stream. But who cares? Because the point of this is that by very simple changes, you can make things run n times faster, where n is the number of cores, just by going from sequential to parallel. So the infinitesimal slowdown you get by using streams when you run them sequentially is more than made up for when you move to parallel stream, which is good. So let's kind of visualize this and see what's going on. This will be the processStream method. We'll look at that one first. And so that searches a list of input strings in parallel, where the input strings are the works of Shakespeare. So you're given a list of input strings to the processStream method, and it will convert the collection, which is an array list of works of Shakespeare, into a parallel stream. So you'll have substreams with chunks of input strings. And of course, it'll end up with each one being done individually at the atomic level, where atomic in this case just means there's only one of them. You can't subdivide things any smaller than one element in an array. What comes out of parallel stream will be a stream of strings. So you can see we went from a list of strings, the green thing corresponds to the list, to a stream of strings, and then these input strings can then be processed in parallel on separate threads and cores as part of the common fork join pool. The next thing we do is we apply the map intermediate operation, passing in the processInput method reference. And that's the other method we're about to talk about. That's the one that really does the searching on each input string. And what happens there is that processInput will look for all the phrases in each input string in parallel. So we'll see how that works in a second as well. What comes back from this, because processInput converts from a string to a list of search results. So we have coming into processInput will be a string, which corresponds to the input string we're looking at, like Macbeth or Hamlet. And what comes out of this will be the list of search results, all the things that matched in that particular element. And so what we get back here then will be the list of search results. And some of those lists of search results may be empty if none of the phrases match the input string. So let's say you were only searching for famous Hamlet quotes, but you looked in the entire works of Shakespeare to find those. Well, obviously, you're not going to find many of those famous Hamlet quotes in Macbeth or Julius Caesar or As You Like It or whatever. So those lists will be empty. And we'll do some special cool things with empty lists later to get rid of them using other stuff like flatmap. What we end up with here will be a stream of lists of search results, and we collect that to a list. So we'll end up with a list of lists of search results. And when collect is called, remember that terminal operations have the responsibility of triggering all the other processing. Remember we talked about before how streams work by building up this linked list of nodes, and when the terminal node is hit, then the processing starts to go in earnest. And so it'll trigger the intermediate operation processing to run on the multiple worker threads and cores that are part of the common fork join pool. And then we end up with a list of lists of search results. And that list of lists of search results will be ordered in so-called encounter order. And that's the order that the original works of Shakespeare were processed. So again, assume it was alphabetical for lack of a better term. So in that case, Hamlet would come before Macbeth, which would come before Twelfth Night, and so on and so forth. And that's just saying that by default, you get the ordered on ordered collections like lists in the same order. You get the output in the same order as the input was looked at. So just kind of pointing that out. Let's now talk about how to visualize the process input method. This is the one that is used to find phrases in an input string in parallel. So for each input string, for Hamlet, for example, we take a list of phrases and we go ahead and convert that list of phrases into a parallel stream. So now we end up with a bunch of chunks of those phrases, one chunk per phrase. And then we end up with a stream of these phrases. So we have a stream of phrases for a given input string. And these will then be processed in parallel. And what we're going to do here is we're going to take each of those phrases and we'll use the map intermediate operation. And we're going to go search for each phrase in that given input string, because process input is called in the context of a particular input string. So we'll go ahead and search for each phrase in parallel on a given input string. And what will happen is we'll end up with a stream of search results where the search results indicate whether or not there were any matches, and if there were, where the matches occurred in the input string. And notice how we changed the type. So we went from a stream of strings to a stream of search results. And then what we're going to do is we're going to go ahead and we're going to filter out empty search result objects, because there's no point in passing them up the chain because they're empty. So filter will only let non-empty elements come through, and what we'll end up with when all is said and done is a stream of search results, and this stream of search results could be empty if there were no matches. Kind of said that before. And then the last thing we do here is we collect that stream of non-empty search results into a list. So collect, again, triggers the intermediate operation processing. List is what gives us the particular data structure that is used to collect into. That's what the collect method returns as part of the collector framework. And again, the results will be based on encounter order. So if the phrase neither a borrower nor a lender be occurred before to thine own self be true, or get thee to a nunnery, or whatever your favorite Hamlet phrase is, if it occurs in that order, that's the order that they'll occur in with the output. And the list will be completely empty if none of the phrases match the input string, and that'll get removed later when flat map is used. Now, keep in mind, again, that just as a side note, even though it looks at some level like the processing is done from left to right, top to bottom, it's actually top to bottom, left to right. So each of these different, I call them slices or paths through the pipeline of operations will be run in its own thread in the common fork join pool, and all those things will run in parallel, or could run in parallel depending on how many cores there are, and they each time will pull the data all the way through from the source to the terminal operation. So it's kind of a little confusing at first, but the reason for doing this is severalfold. First of all, it allows for short-circuiting operations to do the absolute minimum amount of work, which is important if you need short-circuit operations, which we don't here, but you might in other cases. And number two, it integrates with something called integrated layer processing, which is a way of being able to ensure that all the processing that takes place is within one thread, thereby maximizing thread affinity and minimizing the need to invalidate caches between different processor cores. So those are the reasons why Streams works in the way it does, from top to bottom, left to right, instead of left to right, top to bottom. So that's the end of the visualization of these methods. What we'll do next, of course, is see how the code works and talk a bit more about the code.